Welcome, everyone. Thank you for coming to our presentation on Nexus, an instant GraphQL framework. My name is Felicia, and I'm joined by my teammates, Kim, Ben, and Matt. Together, we built Nexus, an open-source GraphQL framework. Here's Nexus in a nutshell. We take a user's existing data sources, generate a GraphQL API, and deploy that API to the cloud so that all the user's clients can make requests to a single endpoint. Nexus helps with the middle part of this diagram, building and deploying the server quickly. Before we dive deeper into Nexus, we'll talk about REST APIs and some of the problems that have led to the use of GraphQL. Next, we'll discuss the challenges developers face when they implement a GraphQL API and some of the existing solutions. Finally, we'll share why and how we built Nexus and the decisions we made along the way. Now, let's jump into APIs. When we decouple parts of a system to separate concerns, we need a way for those parts to communicate in a standardized way. An API, or Application Programming Interface, serves as that link. The most common API pattern today is REST. A RESTful API provides endpoints corresponding to an application's significant resources. One reason for its popularity is that REST is simple for developers to build and understand. REST particularly shines in CRUD applications, where client pages correspond directly with REST endpoints. However, issues can arise when a new client use case with different data access patterns needs to integrate with an existing REST API. Each client type has different data needs, so a fixed endpoint may not serve both at the same time. Overfetching is when one client receives too much data that it won't use. Due to a mobile device's limited screen size, fewer details can be displayed on this example catalog page compared to the desktop application. This means less data is needed from the API to load this page. Fetching too much data can lead to a user experiencing higher response times, resulting in a slower page load. Fetching too little data, or underfetching, can also be a problem. When an endpoint doesn't contain all the required data, the client must make additional requests. This can cause a waterfall effect, resulting in multiple round trips between the client and server. Round-trip latency from additional requests can significantly increase page load time. This is especially problematic on mobile devices, where a typical page takes 88% longer to load than on a desktop. Beyond application performance, overfetching and underfetching affect how front-end developers spend their time. When an API is not a good match for the front-end client's data needs, developers must spend additional time figuring out how to fetch data, filtering over unnecessary data, and orchestrating many API calls. In some cases, dealing with data can take the majority of front-end development time, leaving little time to spend on building critical UI. Fortunately, development teams faced with supporting multiple clients are not limited to using fixed endpoints that cause underfetching and overfetching. They can adapt their REST APIs to make their endpoints fit each front-end use case. One option is to add a new endpoint that will only return the data necessary for a particular use case. Another is versioning the API for each use case, providing separate sets of endpoints for each type of client, with data returned based on the needs of that client. A third option is allowing clients to customize a request with query parameters. While customization can make a REST API more flexible, it can also make it more difficult to work with. In 2015, GraphQL emerged as an option to create APIs that are highly customizable and flexible to handle many different clients. Several key factors can lead a team to adopt GraphQL for their API. When they need to support multiple front-end clients that have different data access patterns and different bandwidth needs. When data access is nested, interrelated, recursive, or when it varies frequently. Or when data is distributed across many different sources. So, how is GraphQL different from REST? A REST API exposes many endpoints that correspond to resources. In contrast, a GraphQL API exposes a single endpoint. This difference contributes to many of the benefits GraphQL can offer. Each front-end client uses this single endpoint to request all the required data. Front-end developers no longer need to keep track of many different endpoints and their standards. Back-end developers no longer need to add new endpoints, adapt their endpoints, or version them for different client types. With a single endpoint, the source of data is simplified. But how does GraphQL support fetching multiple resources for different client types using a single endpoint? By introducing a query language that clients use to request the data they need. Queries are customizable, and the same query can fetch multiple resources at once. The response will contain precisely the information requested, no more, no less. In fact, query language is the QL in GraphQL. Here is a simple query. This query requests a book resource by its ID. In addition to the type of resource, we also get to decide which fields related to this resource we would like returned. Here, we're requesting the title, page count, and author, specifically the author's name. When we send this query in an HTTP request, the response from the GraphQL API matches the structure of our query. This means our mobile client can query for one set of data about each book, while our desktop client can query for a different set of data about each book. This helps front-end developers save time and reduces the amount of data sent over the wire. Now, let's recap what we've discussed so far. APIs help to standardize communication between parts of a system. REST is the most common API pattern today, but problems like under and overfetching can degrade performance and impact developer productivity in some cases, like adding a new mobile application. GraphQL was introduced to address these problems. A GraphQL API exposes a single endpoint, allowing different clients to request the data they need via customized queries. Now, I'll hand it off to my teammate Kim, who will discuss GraphQL implementation challenges.
Thank you, Felicia. So while the front-end developers enjoy the benefits of a single endpoint, the responsibility for supporting a GraphQL API falls to the back-end team. Building a server that integrates multiple data sources into a single endpoint can be a challenge for small teams who have limited resources or are brand new to GraphQL. First, developers must get up to speed on the GraphQL specification and learn about the unique components that make up a GraphQL server. The learning curve with this can be steep because GraphQL differs significantly from REST. They'll also need to decide on approach to writing their schema. Each approach has its own trade-offs, which can complicate the decision and slow down the setup process. Secondly, they must deploy their new server so that the front-end clients can query the API. They need to decide which services to utilize among the many options, provision and connect their chosen services, and deploy and manage that infrastructure. There are many steps that go into building and deploying an initial GraphQL server, and this process can be time-consuming, tedious, and error-prone. Nexus was built to address these issues for small teams who want to get the benefits of GraphQL with less of the initial overhead of setting up their GraphQL server and deploying it to the cloud. To understand the challenge that developers face while building and deploying, let's first look at the components that comprise the GraphQL API on the server. The main components of a GraphQL server are schema and resolvers. A GraphQL schema defines the data types that can be requested and the relationships between types. Resolvers are functions that retrieve the requested data specified in the schema. A type definition describes a queryable type within the GraphQL schema. Each type includes fields which define the properties of that type, and each field can be a base type like string or integer. Fields are also used to represent association between types. For example, a type of book may have a field author, which corresponds to an author type, thus associating these two types. Resolvers are functions that fetch the data for each field in the query. They specify how the data for fields in the type definitions are retrieved. Before developers can create a schema, they may choose between two approaches for schema writing: schema first or code first. The schema first approach utilizes the GraphQL schema definition language, or SDL for short. Using SDL allows a developer to define their schema in a programming language agnostic way. Since the SDL is not tied to a specific programming language, the resulting schema is an outline of the data model that lacks implementation details. In a schema first approach, the resolvers are written separately in the developer's chosen programming language. However, this approach involves a new language, and the SDL-defined schema is not complete on its own. The separation of resolvers can lead to duplication, requiring more maintenance over time. For a code-first approach, the process begins with defining types, along with the resolvers and a chosen programming language. In this approach, the code serves as the schema. The code-first approach is self-contained, which means the entire schema is defined in one place instead of divided. Regardless, in code form, the overall structure of the data model is more difficult to quickly understand. Additionally, the complexity of a schema grows as multiple data sources are added. Many teams will opt to modularize their schema, separating each data source into its own schema. They will then need a strategy to combine them into a unified schema if they want to maintain the benefit of a single endpoint. So we've talked about a few challenges facing developers as they begin to learn how to build a server in this new paradigm. But building the server is only half the battle. The developer still needs to deploy it in order for the front-end team to make queries to it. This process can be complicated and involves many steps. When deploying to the cloud, there are a variety of platforms a developer might choose. We focus on the most popular: Amazon Web Services, also known as AWS. Here is a list of resources that need to be provisioned in order to deploy a basic server on AWS. Each resource is provided from a different AWS service. Deploying on their own, a developer will need to understand these AWS services and the resources they offer, as well as choose the right ones to support their architecture. These resources must also work together, and coordinating communication between them can introduce bugs that are difficult to troubleshoot. This can be tedious for the developer and increases the time spent to get a server running for clients to query. Currently, AWS offers 200 plus services, with more added all of the time. The sheer volume of services, plus their confusing names and acronyms, has confused so many developers that they started writing AWS in plain English articles. These articles strive to explain what each service is used for and what it should have been called instead. So to assist the developer in provisioning resources, AWS provides a few different tools. First is the graphical user interface that is used for provisioning resources by hand. Next is a command line interface that can be used to provision resources by interacting with their API. Both of these tools strive to make provisioning convenient for the developer. However, they both involve dozens of sequential steps to provision and then connect all the different resources required. In the slide shown, you can see an example of the commands that need to be run in the AWS CLI to provision a single EC2 instance. This is a simplified example. The AWS CLI documentation for EC2 alone offers 575 commands. This volume is what developers struggle with. Although having many options can be good, it can also be hard to navigate them, especially for someone new to infrastructure. To recap, developers brand new to GraphQL will need to get up to speed on the GraphQL spec. This includes the schema definition language, type definitions, and resolvers. They'll need to research and weigh the pros and cons of each schema writing approach. And as they add multiple data sources, they'll look at how to modularize the schema and then recombine them into a unified schema. Additionally, they need to understand the many different cloud services needed to deploy their server. The process of combing through hundreds of confusingly named services with thousands of commands and configuration options to provision cloud infrastructure compounds the API setup process. Now, large organizations can often afford to dedicate teams of developers to learn the GraphQL specification and implement their API in-house. On the other hand, smaller organizations may decide early in their initial research that the complexity which GraphQL brings outweighs the benefits. Besides the performance benefits, the secondary goal of switching to GraphQL is to save developers time. So, if the time spent getting the API running is more than the time saved on the front end, switching to GraphQL will not appear to be worth it. Small teams can benefit from an alternative to building their own GraphQL API. As they explore the GraphQL ecosystem, they will find several existing solutions that can help make the process faster and easier. Now that we've discussed GraphQL implementation challenges, I will turn it over to my teammate, Ben, to talk about existing solutions and where Nexus fits in with them.
Thanks, Kim. The use case we had in mind while building Nexus would have a few general requirements. An existing solution would need to allow the developer to set up the server in just a few minutes, as well as combine multiple data sources into a single endpoint, since data is frequently distributed across several services. Assisting with deployment would speed up the process further. Finally, it should be extendable to accommodate future needs. At the highest level of abstraction are managed cloud services like Hasura and StepZen. These are GraphQL API generators that automatically create, manage, and deploy the server for the user. Setup can be done in just a few minutes. Previous knowledge of GraphQL isn't required to get an API running. Most managed services support a wide variety of data sources and offer the ability to combine data sources into a unified GraphQL layer. They may not support every source, so developers must ensure that those that they use are currently supported. Deployment is handled entirely by the service. This is a primary benefit. Outsourcing deployment results in a lack of control over the infrastructure that supports the API and no opportunity to optimize the cost of that infrastructure. The abstraction of both server generation and deployment makes it challenging to extend a managed service. For example, adding a data source that isn't directly supported may not be feasible. Managed services typically offer a robust set of additional API optimization features like caching, monitoring, and observability. A managed service abstracts much of the complexity away for the user, leading to speed and ease of setup. However, they trade off extendability and control. Developers who want additional control and extendability can use several open source GraphQL API generator libraries, like WonderGraph or GraphQL Mesh. Generator libraries help to get developers started more quickly than if they were writing GraphQL code from scratch. They still require manual setup and configuration, which often involves some basic GraphQL knowledge and library-specific syntax. Generator libraries support a wide variety of data sources. And they are also highly extendable because the developer has access to the code that is generated. For sources that aren't supported, they offer the ability to extend the schema manually or with plugins. Plugins are also used to add advanced features. For those that aren't offered directly, the code can again be extended manually. While library documentation might include some basic deployment guides for different cloud providers and architectures, they don't typically provide direct assistance with deploying a server. Without deployment assistance, developers have full control of their infrastructure decisions and cost. But this comes at the expense of the developer's time and the deployment complexity that Kim was just talking about. We built Nexus to serve as a framework for quickly generating a GraphQL API from multiple data sources and deploying that API to a user's AWS account. We wrap several open source tools for API generation and deployment, speeding up the configuration and use of those tools. Nexus uses GraphQL Mesh, a powerful GraphQL API generator, to build the user's server. We reduce the configuration of this open source library to a few simple commands, so no experience with GraphQL or the Mesh library is needed to get started. Nexus currently supports 3 data sources. Users can add their existing Postgres database directly to their generated GraphQL server with only their Postgres connection string. They can add internal and third-party REST endpoints using a JSON file that follows the Open API specification. They can even add other GraphQL APIs to their server. For data sources we don't currently support, the user can extend their API using Mesh's collection of additional sources or by manually extending the schema. Nexus deploys the generated GraphQL server with a single command. We make deployment simpler by abstracting infrastructure setup and making a few decisions for the user. The deployed infrastructure is provisioned entirely in the user's AWS account and is fully modifiable by them. Nexus doesn't offer advanced features for fine-tuning the API like managed services do. However, users are free to add features as needed because the generated code lives on their local machine. Nexus offers users some of the benefits of extendability and ownership that come with an open source library, along with some of the deployment abstractions of a managed service at the cost of advanced API features. We built Nexus for teams who would like to build and deploy a simple GraphQL API in just a few minutes, with the option to extend it over time. By simplifying the setup process, we save developer time and make open source generator and deployment tools simpler to use. We abstract the deployment process while using a user's AWS account. The code that Nexus generates is user extendable to add new data sources and other API features as needed. Now that you've learned a little bit about Nexus, we'll demonstrate a few of the features we've built to show the process of going from zero to deployed GraphQL API. First, we'll take a look at setup and building the server. Nexus is available as an NPM package. Global installation gives a user access to all the commands and a local admin dashboard. After installation, the user can initialize a new project with the init command. They'll run this in an empty project folder where we'll generate their server files. We collect an initial Postgres database as the primary data source. To avoid confusing bugs later on when the server is generated, the Postgres connection string is validated for a user when they input it. And the user now has a basic GraphQL server built from their Postgres database from a single Nexus command. Let's take a look at adding a second data source, a few endpoints from a REST API. Adding the REST endpoints is similar to adding the Postgres database. The user provides the local or hosted location of a JSON file that defines their endpoints following the Open API specification. Adding a GraphQL data source is similar. Now that the user has multiple data sources connected, it's time to start the API locally and test it. The dev command opens a graphical interface for exploring the unified schema and making test queries. This test server is identical to the API that will be deployed, so it can be used to accurately pre-plan client queries. While the server generated and tested, it's time to deploy. Nexus simplifies the deployment process down to a single command, Nexus deploy. All the complexity of packaging the server code and provisioning the infrastructure is handled in the background by this command. After a few minutes, the server is deployed to the user's AWS account. They'll get back a URL in the command line that they can then use immediately to query the deployed GraphQL server from any of their front-end clients. Now that the server is deployed, the user can run the dashboard command to start a local dashboard that displays information about their server and advanced configuration options. This includes the server status, the endpoint, an authorization key, and data sources that they've added. Users can also add, edit, or delete data sources. A local development server is also provided here for testing. After changes are made to the data sources, a helpful message will alert the user to redeploy so that the deployed server is up to date. Redeployment can be accomplished here in the dashboard with a single click or with the Nexus redeploy command. If the user wants to remove the provisioned infrastructure at any time, they can use the destroy command to deprovision all AWS services that have been set up. Since the infrastructure is deployed to their account, they can make changes directly within the AWS console. The destroy command ensures all services are removed at once, so that they are not charged by AWS for services that could be missed with manual deprovisioning. Now that you've seen how Nexus can help save users time, we will go behind the scenes and explore how we built it. My teammate Mac will cover Nexus architecture, as well as some of the development challenges we encountered along the way.
Thanks, Ben.
I'm going to go for it.
Sorry about that. To start, here's a diagram of the Nexus architecture that we'll be discussing in this section. We can illustrate the Nexus workflow in two parts, creating the GraphQL API server and deploying it. First, let's look at how we create the GraphQL API server for the user. Nexus wraps the open source tool GraphQL Mesh to generate schemas and combine them into a unified GraphQL API. The main point of interaction between Nexus and GraphQL Mesh is through a configuration file where YAML is used to specify a variety of options. When a user interacts with the Nexus command line tool, they start by entering the init command. Behind the scenes, this command first installs necessary GraphQL Mesh packages and creates a configuration file in the user's current working directory. Nexus prompts the user for a Postgres connection string, which is then validated by using the PG promise library to make a connection to the database. The validated database connection information is then passed to a template where we format it for the user into valid YAML and then supply it to the configuration file. Additional data sources are added to the configuration file through the add command. The user provides data source information to Nexus, which is then formatted into YAML and supplied to the configuration file. Once the data sources are added, GraphQL schemas can be created for every data source supplied to it. Each data source is consumed by a source handler, which introspects or gathers information about the data source. The result of introspecting each data source is an individual GraphQL schema defined using the SDL. These schemas can be viewed in the user's project directory. The generated schemas are then combined into a unified schema. Schema customization in the form of transformations can be implemented at both the individual and unified schema level. For example, we add an authorization middleware function to the unified schema for the user to prevent unauthorized access. Once the schemas are generated and combined, and any modifications applied, the local GraphQL server is ready to deploy. Next, we will look at how we deploy the server for the user. Since we generate the GraphQL server on the user's local machine, we need a reliable way to deploy their application code and ensure that it runs on their AWS infrastructure. We chose to deploy the user server using containerization. Let's briefly discuss the process and clarify a few terms. Nexus writes the GraphQL server code on the developer's machine. This application code has dependencies that also live on their machine. If the application is transferred to a new machine, errors may occur due to application dependencies not being present. Containerization encapsulates the application code, libraries, and dependencies that are required for the software to run. Doing this allows the application to be run on many different systems while reducing dependency issues. Docker is an open source implementation for containerization. Some key Docker terms include images, image repositories, and containers. A Docker image is like a blueprint of the application, which includes all the dependencies. We store Docker images in a repository, similar to how we store source code on a remote repository like GitHub. Containers are created through images and run the actual application code. We can pull the Docker image from a repository onto a cloud machine to run the application. For Nexus, creating and pushing a Docker image to a private repository, pulling the image down onto cloud infrastructure, and running a container from the image provided us a code deployment workflow that helped eliminate application dependency issues between the user's local machine and the cloud-hosted machine. When the user runs the deploy command, we provision the AWS services to get their server up and running. We start by locally building a Docker image from the generated GraphQL API server. Next, we use Terraform, an infrastructure as code tool, to create a private image repository on Amazon's Elastic Container Registry. We considered using AWS's Service CloudFormation as an alternative, but decided against the proprietary tool in order to offer multi-cloud deployment in the future. We then use the AWS CLI to push the Docker image to the newly created private repository. We also use Terraform to provision AWS Elastic Container Service and Fargate. Elastic Container Service makes managing and scaling containers easier. Fargate works alongside to provision and manage all the infrastructure that is required to run the container, meaning the user will not have to directly manage the underlying EC2 instances. Together, they allow the developer to spend less time managing resources, but still allow them to make changes or scale in the future. Additionally, Nexus handles the setup of related infrastructure components such as virtual private cloud, subnets, internet gateway, security group, router, and routing table. Here is the user's high-level AWS architecture after deployment is complete. We'd now like to highlight a few of the technical challenges we encountered as we built Nexus. Part of the reason we developed the dashboard was to facilitate some advanced server configuration that would require many steps if done at the command line. We'll walk through one configuration option we implemented, connecting data across sources. As the user makes some of these changes in the dashboard, they'll want to test them quickly. We needed a way to ensure the local test server was always up to date with the current configuration. Finally, when changes have been made and tested, we want to ensure the user will redeploy their changes to their deployed architecture. Let's jump into why a user might want to connect data across sources and how we help them accomplish this. Here's the basic setup after a user has initialized their Nexus project. They now have a GraphQL API that each client can query for the data they need. While each data source has been combined in the unified schema, there's still a problem. Data stored across multiple sources is often related. An example could be product data, such as books stored in a database, with cart information stored in Shopify. When separate data sources contain related data or combined in a generated server, the relationship across sources isn't automatically recognized. We can still fetch information from both in a single query. However, the relationship that exists between the two sources isn't represented in our GraphQL API. This slide shows a query with the cart field from one data source and the books field from another data source. When the relationship isn't defined in a GraphQL API, overfetching can occur. One of the main problems we're trying to avoid by using GraphQL in the first place. Since we can't shape a query that shows a relationship between the two data sources, we retrieve a response that has all the data for one cart and data for all books. The front-end developer would then need to filter only the books that are required for this particular cart. Our challenge was to find a way to help the user define these inherent relationships between data sources within their GraphQL server. If we can connect these data sources, they can be queried together as shown here. Fetching a specific cart would yield only the books for that cart, even when books come from another source. In order to associate two data sources, we needed to capture a few pieces of information. We gather this from the user with a form on the dashboard. This form is built dynamically and pre-filled with available options based on the user's generated schemas. We need to know which types from two data sources that the user would like to associate. To display these, we need to load all the individual schemas and filter only the relevant types in each one. This ensures the user only sees valid options for types that can connect on the form. Here, we'll use a cart and books to demonstrate. Once we know the two types, we can display the available fields for each of those types for the user to select. These fields should represent the data association, typically an ID field stored in both data sources. In our example, the cart's book ID field is directly related to the ID of a book. The user knows this, but our GraphQL server doesn't know this. Once we know how the data is associated from the user's selections, we can build the necessary connection with the GraphQL schema. Here's what the process of building the connection to the schema looks like. First, we add a new field to the user's cart, a book. In the background, we extend the cart schema by adding a new field to the cart type with a custom type definition in the user's configuration file. This defines the association within the GraphQL server and will allow the user to request books related to a particular cart. Next, we need to define how we resolve this new book field. We accomplish this by adding an additional resolver within the user's configuration file. Now, when the user queries a cart and selects the book field, the correct book data is returned. When the user makes a change to the server on the dashboard, like connecting two data sources as we just seen, locally testing these changes is a logical next step. To assist with testing, we run a local development server that is accessible within the dashboard. However, GraphQL Mesh offered no option for hot reloading this development server. We needed a way to keep the server up to date without forcing the user to shut down their dashboard every time they make a change. So we implemented our own hot reloading function. Anytime the user makes a change to their server, such as adding, editing, or deleting a data source, the change is reflected in their configuration file. We use the watch function from Node's file system library to keep track of changes within the configuration file. When there is a change, we kill the running development server and load a new one. By implementing this simple hot reloading function, we avoid outdated information in the user's test server and prevent them from having to shut down the entire dashboard anytime they make a change to their server. In addition to reloading the dashboard's local development server on user changes, we needed a clear redeployment workflow. As the user shifts their focus from configuring to testing, they may forget to redeploy the changes they made. To help remind them that their local server is out of sync with their deployed server, we implemented a basic change notification system. We created a helper function within the dashboard's backend that is invoked on every user change. This function updates an environment variable in the project folder that tracks changes. We included logic in our React code for the dashboard that displays the alert if changes have been made and if there's an active deployment. If no server is deployed or no changes have been made, there's no need for redeployment, so the alert is not visible. When there are changes in a deployed server, the alert is visible and the user can click the corresponding button to initiate redeployment. After they initiate redeployment, we lock the dashboard's deploy and redeploy functionality until it's successful. In the background, the Docker image is rebuilt locally. Once the image is ready, we use the AWS command line to push the new image to the user private image registry, and then update Fargate to utilize the newest version of the image. Finally, we wait for a successful deployment and update the user's dashboard to reflect the status. I'm now going to hand it off to Felicia to close us out.
Thanks, Matt. We built Nexus to serve as a framework for generating a GraphQL API from multiple data sources and deploying that API to users' AWS account. Nexus offers users some of the benefits of extendability and ownership that come with an open source library, along with some of the deployment abstractions of a managed service at the cost of advanced API features. By simplifying the setup process, we help developers save time and make open source generator and deployment tools simpler to use. And that concludes our presentation. Thank you everyone for joining us. We really appreciate your support. So we will now open up to a Q&A for any questions you might have.
And luckily, we already had a couple questions come in the middle. Justin from the Synapse team, which is a GraphQL project from last year's Capstone, has a couple of questions in here. The first one is, what are some of the tools that you use to create the new GraphQL unified schema or the individual schemas from the different sources? Or did you code that yourself? Matt, you want to talk a little bit about how we got to GraphQL Mesh and some of the steps we looked at along the way? It was a pretty interesting journey.
Sure. Yeah, so I think naively, we tried to initially code that up ourselves, like a GraphQL schema generator based on some database information. But we decided to move on from that just because it would have taken a lot more time. So then we researched more, and then we found another open source tool, PostGraphFile, which was a GraphQL schema generator based on Postgres. And that was a good step in the right direction, but it didn't offer us the schema generation from other data sources. So we put that to the side, and then more research, we found Mesh, GraphQL Mesh, which generates schemas from multiple different data sources. So that was just the right fit. So we stuck with that open source tool.
Nice. And Justin's second question is, did you create a way for the user to enter the data association and then auto create resolvers? I think we touched on a little bit of this, but maybe we could dig in a little bit more. We do auto generate resolvers. We started with just Postgres connections, and it was pretty interesting. We didn't get to chance to talk about this because it got a little bit more in depth, but we ended up basically, when we connect data sources, we have the tendency to create a new problem, an additional problem once those two fields are connected, and we're starting to request data from multiple sources within the same nested query. And so there's an N+1 problem that gets created where we're fetching data from a cart that returns, say, 3 books, and then we go fetch each one of those books individually from the second data source. So we ended up having to implement some filtering options and some additional configuration for a transformation along the way from individual schema to unified schema that would allow us to add an additional resolver just to get the data we needed from the source to ensure that it was there and we didn't create that N+1 problem for the user. But then ultimately, yeah, we are auto creating resolvers that don't exist from the originally generated schema. Is there anything you want to add to that, anybody?
No, I think you captured that really well.
Yes, I think it's
Awesome.
great.
Ashish, how's it going? Great work. You mentioned extendability as a concern when comparing solutions and creating Nexus. What kind of use cases can afford to ignore extendability? Is it only for schemas that aren't likely to change, or are there other factors? Anybody want to take
That's a really
this one?
great question. Yeah. I think you pretty much encapsulated it. So if the team knows what they're going to need in the future, then they might not need extendability, right? So if they go for like a fully managed service, and let's say they support Postgres and that's all they have, and they're like an established team and they know they won't need Postgres in the future, that could be an option. But let's say you have a smaller team that's just starting out, and maybe an example would be something like they're slowly getting bigger, right? Like they're slowly getting bigger and they don't know if maybe they'll need to incorporate another GraphQL API or a MongoDB database, for example, in the future. Then extendability would be really valuable to them in that regard. Does anybody have anything to add to that?
Oh, I think that was it. We looked at a couple of managed services that had, coming soon on their website for data sources like MongoDB, like you're saying, Kim. And then we looked at articles from them from 2 years ago that said coming soon, MongoDB. So it's instances like that where you really give up your control completely to the service and hope that they'll support it. Of course, you could of course like generate a separate API from another service that supported Mongo. But then you're either having to port over all of the settings and the setup that you've done in one service to that second service, or then operate 2 services separately and have 2 different endpoints. So we kind of kept that in mind when we were thinking about this idea of extendability. Thank you, everybody, for coming. We really, really appreciate you being here, and so glad to get to share our project with you all.
Yes.
Yeah,
Thank
thanks
you,
everyone.
everybody.
Thank you.
Have a great day.
Have a great day.
Bye.